Okay, we want to continue with our discussion of things related to the subject of light. Now, in the previous part of the lecture, I talked about having parallel rays of light come in and interact with a mirror, for example. I want to talk about what we mean by that when we say parallel light. And so you can imagine if you have a light source, we know that the light waves are going to be traveling out spherically. And of course, if this were like waves on a pond, they'd be traveling along the surface as circles. But if you're talking about something like light that's being emitted into a three-dimensional space, if I make a spark, the light from that spark is going to be traveling out in every direction. And of course, we know that these rings represent the crests of the wavefronts of the light waves. Now, what we mean when we talk about parallel light, if I'm close to the source, and let's see, I've got another ray that I've drawn here. So I've got a point on a wavefront right here, and a point that's close to it, and they're going to be going radially out from the center of the source of the wave. And you can already see that these waves, the rays coming from the center, even though right now they're close together, they're spreading apart. They're getting farther and farther apart so that those rays are not parallel. But you could imagine if I draw some more rays, and I'm not drawing the whole circle, but I'm drawing part of it, as I get farther and farther away, if I pick 2 points that are close together to one another, the rays, when they go out, they're not going to spread out as much. The further away you are from the source, the less spreading you get. So if you're very, very far away from the source, the wavefronts would all look parallel to another. Now, of course, these would be parts of a really big circle because it's very far away from the source. But if you're far enough away and you're looking at just a small portion of the wavefronts would all have lines that go parallel to one another. The rays, so if I pick a point here and another point close to it, those two rays traveling with that wavefront would be moving parallel to one another. And that's what we mean when we say that the light is parallel light. The next thing that we want to talk about is refraction. Now, you'll remember hopefully that refraction is actually a property of the waves, and including sound waves and water waves and electromagnetic waves, any kind of waves can refract. And if you remember, refraction is a bending of a wave when the speed of the wave changes because it has transferred from one material into another material. And we talked previously about an analogy using a lawnmower that, if you're pushing a lawnmower on a pavement, it's going to be going, the lawnmower will go faster, but when it hits the grass, it's going to slow down. And if it's coming in at an angle, this wheel will slow down faster than this wheel, and so the lawnmower will turn. And once both wheels are in the grass, there'll be no more reason for it to turn, and it'll keep going straight in the grass, just moving a little bit slower. This is the basic idea of refraction. If you have a wave coming in, this part of the wave will slow down before that part of the wave, and so the wave will bend. And we can see this, the arrows here actually represent one of the rays of light coming in. Now, we can see a more practical picture of that. The ray of light here is coming in, and you can see the wavefronts, and the wavefronts are a little bit further apart because the wave's moving faster. And so what happens when the light wave travels into the water, it slows down. So the wavefronts are not moving as far each unit of time, and because of that, you can see this part of the wavefront is slowing down, but this part is not slowing down, so the whole wavefront is going to tend to bend at the interface or the boundary between the air and the water. But once all of the wave is in the water, all of the waves are traveling parallel again. And this blue line here represents the sort of one ray on this wavefront, and we can see that every particular ray will behave the same way. It'll come in going straight, and once it hits the water, it will bend. And again, that bending due to a velocity change as light or any other wave goes from one material into another material, that bending is called refraction. Refraction. Now, if you remember, we talked about how to measure the angle that a ray of light is coming in when it strikes a surface. When we talked about this, when we talked about light reflecting off of mirrors. And we said that the normal way to measure the angle of light is to the imaginary line that's perpendicular to the surface, and that's called the normal line. Incidentally, I don't know if I mentioned this or not, but in the context of mathematics, the word normal often is just a synonym for perpendicular. So they could have called it the perpendicular line, and that might have maybe been easier to remember, but for whatever reason, they call it the normal line. And again, that's just a term that comes from mathematics. It just means perpendicular. So this imaginary normal line is perpendicular to the surface of the water, and I've got the incident ray of light coming in at a particular angle. The angle is to the normal line, and then when it enters the water, it bends. And it bends again to an angle that you would measure to that normal line. The next thing that I want to talk about is something called the index of refraction, and that's right here, the index of refraction. And it's usually represented by the letter N, and what it is it's the speed of light in vacuum, and by the way, that's the fastest that light can go. Remember, we talked about how when light passes through a material like glass or water, it gets absorbed and re-emitted, and in that process, it slows down while it's passing through the material. And so when light is moving in the vacuum of space, it's moving at the fastest it could possibly move. When it enters the Earth's atmosphere, it slows down a tiny bit. If it goes into some water, it slows down even more. If it goes into glass, it slows down even more. And so light travels at a particular speed in every material that it can go through. Of course, remember, light doesn't transmit through every material, but it does transmit through some. And if you tell me diamond or glass or water, all of these light's going to have a characteristic speed for it. It's going to always be the same speed in water. It's always going to be the same speed in diamond, etc. And so by comparing the speed of light in vacuum, which is the fastest it could possibly go, to the speed in light of the material, we have a number N which characterizes the material in terms of how quickly light travels through it. And incidentally, normally when you're talking about the speed of light in a vacuum, which is that special number, the number that is the fastest that light could possibly go, it's usually represented by the letter C. And when you're talking about the speed of light in a material, it's no longer C because it's slowed down. So usually we represent that with a V, like velocity is V. And so that's why we say N, which is this index of refraction, is C divided by V. Now, the reason that this N is important is it's actually a part of something called Snell's law. And Snell's law tells you that when light passes from one material into another material, and specifically the first material would have an index of refraction N1, which tells you how fast light travels in that material. The second material would have a index of refraction N2, which tells you how fast light moves in the second material. The relationship between the angles is given by this rule called Snell's law. And it tells you that N1 times the sine of theta 1 is equal to N2 times the sine of theta 2. Now, if you don't know what a sine is, that probably means you've never had trigonometry before. But if you've ever taken a class called trigonometry, which is a math class, then you've probably seen what sines are previously. And you know maybe that there's, if you have a scientific calculator, there's a button called the sine button. And if you want to know what the sine of 30 degrees is, you could just type in 30 into your calculator and hit the sine button, and it would tell you. But this still, even though it's not that hard, it's a little bit beyond the scope of this class because there's not an expectation that you've had trigonometry in order to take this class. So I'm not going to expect you to know Snell's law, but the reason that I mention it is because it's important. If I know what the two index of refractions are for the two materials, I can tell you how much the angle changes, how much the light ray bends. And so I don't expect you to remember the formula for Snell's law, but it's nice for you to know that there is a mathematical relationship that will tell you how the angle changes as light goes from one material into another material. Let's look at an example. This example tells us that water has an index of refraction of 1.33. And if the speed of light in vacuum is given to be 3.0 times 10 to the 8 meters per second, then what is the speed of light in water? So this is pretty straightforward to do. We know that the formula for the index of refraction is given by N is equal to C, which is the speed of light, over V. And actually what we want to find is V. So if we do a little bit of algebra, we would solve for V, and that would give us that V is equal to C divided by N. And so now we know that, we can simply plug in the numbers. We can say that the velocity of light in water is going to be the velocity of light in vacuum, that's our C, 3.0 times 10 to the 8 meters per second, 3.0, and then that's going to be divided by 1.33, and that would give you 2.56 times 10 to the 8th meters per second. And that's how fast light would travel in water. And of course we know the 3.0 times 10 to the 8 meters per second is how fast light would travel in vacuum. So we see indeed when the light enters into the water, it does slow down because 2.56 is less than 3.0. Now we can look at some examples of consequences of this fact that light bends when it travels from one material into another. Now you can see sort of a classic idea here that is shown in a lot of physics books. If you have a fish, for example, that is underneath water, and you're above the water and you're looking at the fish through the water, the fish will appear to be in a different location from where it actually is. And so the way we can explain that is imagine some light rays coming from the fish and going into your eye. So the light rays are coming up, and again, this bottom ray is the one that's going into the bottom of your eye. A ray coming at some other angle would go over here and not go into your eye. So these are the outside rays that are actually going into your eye. And so this bottom ray comes in, and when it goes from the water to the air, it bends. And so the same thing happens to the topmost ray. It goes through the water and then it bends, and then both of these rays enter into your eye. Now, just like it did with the plane mirror, your eye and your brain interpret these incoming rays of light, and it basically calculates where those rays have to be coming from in order to be coming into your eye from those angles. And remember, your brain essentially assumes that light rays travel in straight lines, because that's what they do actually. They travel in straight lines. So the two light rays, if you project them back, they actually meet over here, and so the fish would appear closer to the surface of the water than it actually is. And this would be important if you were like trying to go spearfishing or something. You're trying to spear a fish underneath the water. You would be stabbing in the wrong place if you didn't account for this. Here's another example of refraction. When you actually are looking up at the sun and you see the sun in the sky, the rays of light coming from the sun have actually refracted through the atmosphere. So just like the fish, the sun is actually in a different location than where it appears to be, because the rays of light coming in, they get refracted by the Earth's atmosphere. And so that is another example of how this refraction effect can have a real impact on seeing where things actually are.